All right, welcome back to the deep dive. Today we're taking a look at PairVDN, pairwise decomposed value functions. If you're into multi-agent reinforcement learning and you want to see agents actually cooperating, this is an interesting one.
Yeah, this paper really gets into some core problems that you run into when you are trying to do multi-agent reinforcement learning, especially when you're using deep Q learning.
Right.
And particularly in cooperative settings, so you've got all these agents that are trying to work together to achieve some goal. And so, as you're probably familiar with deep Q networks, they can run into some serious issues when you're trying to scale them up to lots of agents.
Oh, yeah, definitely.
So one of the biggest things is this problem of the joint action space just absolutely blowing up in size as you add more agents. So, if each agent has, say, like 10 possible actions, if you have 2 agents, that's 100. If you have 3, that's 1,000. It explodes exponentially.
Right, and it becomes practically impossible to explore all the different possibilities.
Exactly. Exploration becomes a nightmare, right? Like, how do you even begin to search through this massive space of possible joint actions to find the optimal one? It's like finding a needle in a haystack, except the haystack is growing at an insane rate.
Yeah, it's really hard to wrap your head around.
Another big problem is this whole thing with credit assignment.
Right.
So you have all these agents acting together, and they get a single reward for their collective behavior, but figuring out which agent actually contributed how much to that reward, that gets really, really tricky.
Oh, for sure. Especially when they're all learning and change their policies at the same time. It's like, how do you disentangle those individual contributions when the environment is constantly shifting under their feet?
Exactly. That's the non-stationarity problem. Each agent is learning, which means it's changing its behavior, but that means the environment is also changing for all of the other agents. And it just creates this incredibly complex, dynamic learning landscape where it's hard for any one agent to converge to a good policy.
Right. And deep Q learning, which has been, such a powerhouse in single agent settings, it kind of hits a wall when you try to directly apply it to multi-agent systems.
Yeah, it really does. So the fundamental question becomes, how do you even begin to tackle this complexity in multi-agent deep Q learning? Mm-hmm. How do you decompose the problem in a way that's both scalable and allows you to learn effective cooperative behaviors?
Well, this is where PairVDN enters the picture. And, the fundamental idea here, as we've sort of alluded to, is to decompose the value function. And remember that the value function is essentially telling you the expected future reward for the entire team. But instead of decomposing it into individual agent contributions, they propose to decompose it into the combined contributions of pairs of agents.
So you're shifting your focus from what's the value of this individual agent's actions to what's the value created by these 2 agents working together.
Exactly. And their argument is that by looking at things through this pairwise lens, you dramatically increase the system's ability to learn complex and truly cooperative behaviors.
And to actually make this whole pairwise decomposition work in practice, they had to come up with a pretty clever algorithm. They developed this dynamic programming algorithm that's used to figure out what the best set of actions is for all the agents, taking into account this pairwise decomposition.
Right, because it's not as simple as just having each agent greedily pick its best action independently anymore, right? Their actions are all intertwined through these pairs.
Exactly. To really test out their method, they created this custom environment called BoxJump, which we'll dive into more later. And they compared PairVDN against some of the big players in multi-agent reinforcement learning, like VDN, QMIX, and independent Q learning. But let's step back a bit and talk about the history here. What were some of the earlier attempts to tackle multi-agent deep Q learning, and how did they set the stage for PairVDN?
Well, they start out by really emphasizing those core challenges we talked about, those core challenges of multi-agent reinforcement learning in a cooperative setting where everyone shares the reward. Yeah. That huge growth of the joint action space, the non-stationarity problem, and the difficulty of figuring out credit assignment.
Right. They're not shying away from the difficulties here. And they really highlight how DQN, while very effective for a single agent, just runs into a brick wall when you try to scale it up to these multi-agent scenarios with their exploding number of possibilities.
Right. So what were some of the first attempts to kind of crack this nut?
So one of the earliest and most straightforward approaches is independent Q learning, or IQL. As the name suggests, you basically just treat each agent as if it's acting in its own little world, completely ignoring the other agents.
So each agent is learning its own Q function, trying to maximize its own reward, without any consideration for what the other agents are doing.
Exactly. It's simple to implement, But it quickly becomes clear that this approach has some serious limitations, especially in environments where agents need to cooperate to succeed. The problem is that because each agent is ignoring the actions of the others, they end up learning policies that might work well in isolation, but clash terribly when they try to act together.
Right. So, for example, if you had two agents trying to push a box together, they might both learn to push from the same side, which would get them nowhere.
Precisely. And this is a direct consequence of the non-stationarity issue we discussed earlier. Since each agent is learning independently, they're essentially treating the other agents as part of the environment, which keeps changing in unpredictable ways. This makes it extremely difficult for them to learn stable and effective policies.
Okay, so IQL is kind of a naive approach that doesn't really cut it in cooperative settings. What came next?
Well, a key breakthrough came with the introduction of value decomposition networks, or VDN. This was a significant step forward because it directly addressed the issue of the exploding joint action space by proposing a way to decompose the overall value function into a sum of the value functions of each individual agent.
So instead of trying to learn a massive Q function that covers all possible joint actions, VDN essentially says, let's break it down into smaller, more manageable pieces.
Exactly. And the real beauty of this approach is that it allowed for decentralized execution. Since the joint value function is just the sum of individual agent values, each agent could independently maximize its own Q value without needing to know what the other agents were doing.
That makes a lot of sense from a computational perspective.
Yeah.
But I imagine the simple additive decomposition also has its limitations, right?
You're absolutely right. While VDN was a big step forward in making multi-agent deep Q learning more scalable, the simplicity of its decomposition limited its expressiveness. It essentially assumed that the value of the team's actions was just a straightforward sum of individual contributions. And in many realistic scenarios, this just isn't the case.
Right, because sometimes the value comes from the interaction itself, not just the sum of the parts. Like if two agents need to lift a heavy object together, they might both have low individual values, but their joint action creates a much higher value.
Exactly. Or think back to that car crash analogy. The joint outcome of two cars colliding is much worse than just the sum of their individual actions of moving forward. So VDN struggled to capture those kinds of synergistic or negatively impactful joint actions where the whole is greater or worse than the sum of its parts.
So how did researchers try to address these limitations of VDN?
This led to the development of QMIX, which sought to improve upon VDN by using a more sophisticated way of combining these per-agent Q values. Instead of a simple sum, they used a monotonic multi-layer perceptron, MLP. Now, monotonic means that the output of this MLP can only increase or stay the same as the input values increase. It can't go down.
I see. So it's still trying to preserve some notion of individual contributions, but it allows for more flexibility in how these contributions are weighted and combined.
Exactly. And to make things even more flexible, the weights of this MLP weren't fixed, but were actually determined by the overall state of the environment using something called hypernetworks.
Okay, so QMIX was able to represent more nuanced relationships between individual agent values compared to VDN. But the PairVDN paper points out that both VDN and QMIX share a fundamental constraint, this reliance on monotonicity.
Right, and as we've discussed, this monotonicity constraint means they struggle to effectively represent the value of truly joint actions, where the synergy or interference between agents is not simply additive or monotonically related.
So this brings us back to PairVDN and its core idea of decomposing the joint value function into a sum of pairwise value functions. It's like saying, let's move beyond this individual agent perspective and focus on the value generated by pairs of agents acting together.
Exactly. Instead of each agent having its own Q function, you have these functions that estimate the value of pairs of agents taking specific actions together. Mathematically, they represent the total Q value as the sum of these pairwise Q values, denoted as Q tilde ij, where each Q tilde considers the observations and actions of agent I and agent J.
And to create this kind of ring of dependencies, they pair each agent with the next agent in a cycle, right? So agent 1 is paired with agent 2 with agent 3, and so on, with the last agent wrapping around to be paired with agent 1.
That's right. It's like each agent is passing on its contribution to the next one in line. Now, a really important point here is that PairVDN doesn't explicitly enforce monotonicity like VDN and QMIX do. This allows it to learn much richer and more complex relationships between agents' actions.
Can you give an example of how this non-monotonicity plays out in practice?
Absolutely. Let's imagine a scenario where two agents need to simultaneously activate switches to open a door. With PairVDN, you can have a situation where the pairwise Q value for both agents pressing their switches at the same time is very high. But if either agent acts alone, the value is low. This is a classic non-monotonic interaction that captures the essential synergy of their joint action. VDN and QMIX, due to their reliance on monotonic combinations, would have a hard time representing this kind of relationship.
So PairVDN can learn these situations where the value of the joint action is not just the sum of the individual values, but emerges from the specific combination of actions taken by the pair.
Precisely. And while it's not strictly more expressive than QMIX in all theoretical cases, its pairwise structure allows it to naturally represent these non-monotonic interactions, which, as we've seen, are crucial for effective cooperation in many tasks.
Okay, so conceptually, PairVDN seems to have some real advantages. How about the practical implementation? How do they actually go about learning these pairwise key values?
They utilize neural networks, much like in VDN and QMIX, but instead of each network taking the observations of just one agent as input, in PairVDN, each network takes the observations of two agents as input.
So each network is looking at the combined state of a pair of agents.
Exactly. And the output of each network is a set of Q values for all possible pairs of actions that those two agents could take.
That makes sense. They're essentially trying to learn a value function that captures the worth of every possible joint action that the pair could take.
And just like in VDN and QMIX, they can share the parameters of these pairwise networks across all agent pairs.
Right, so you're not learning a completely separate network for every possible pair of agents. You're leveraging the shared structure to make learning more efficient.
Exactly. This parameter sharing allows the system to generalize better and learn faster because the knowledge gained from one pair of agents can inform the learning of other pairs. Now, because each agent's actions are being considered in two of these pairwise terms in the decomposition, one with its predecessor and one with its successor in the cycle, maximizing the overall joint value function isn't as straightforward as it was in VDN.
Right, because in VDN, each agent could just pick its best individual action without worrying about the others. But with PairVDN, things are more intertwined.
Exactly. And that's where their clever dynamic programming maximization algorithm comes in. It allows them to find the best joint action for all agents in a way that's computationally feasible.
So they found a way to manage the added complexity introduced by these pairwise interactions.
Right. The time complexity of this algorithm scales linearly with the number of agents, which is good news. However, it does scale cubically with the number of actions that each agent can take.
So it's still better than having to brute force search through the entire joint action space, which, as we discussed, grows exponentially with the number of agents.
Oh, absolutely. This dynamic programming approach is a key innovation that makes PairVDN practical to implement and train.
Okay, so we've got this new algorithm for learning these pairwise Q values.
Yeah.
How do they actually put it to the test? What kind of environments did they use to evaluate PairVDN?
To really see how well PairVDN could handle coordination among multiple agents, they designed this new environment called box jump.
So tell us about this box jump. What's it all about?
So it's this 2D physics simulation where you have multiple agents, and each agent is represented as a box. The goal is for the agents to work together to reach the highest point possible. They can do this by jumping on top of each other to form a tower.
Okay, so it's all about building a tower of boxes. That sounds like a pretty intuitive way to test cooperation.
Exactly. And the agents get a reward based on the maximum height that any of them achieves. So it's a truly cooperative setting where everyone benefits from working together.
So it's not like a competitive scenario where one agent might try to sabotage another to be the highest.
Nope, it's all about collaboration. And the authors emphasize that they didn't design this environment specifically to favor PairVDN. They wanted to create a challenging task that would really highlight the strengths and weaknesses of different multi-agent reinforcement learning algorithms.
So box jump was their main testing ground. Did they use any other environments?
Yes, they also tested their approach on some existing environments. Simple Spread, and a modified version of Cooking Zoo.
Okay, Cooking Zoo, that sounds familiar.
Yeah, it's inspired by that popular Overcooked game where players have to work together to prepare and serve orders in a busy kitchen.
Ah, I see. So it's a multi-agent version of that, adapted to work with their reinforcement learning framework.
Exactly. They specifically adapted it for the Petting Zoo multi-agent environment platform. And they made some modifications to make it more suitable for their experiments. It's interesting to note that this Cooking Zoo environment has a very high-dimensional observation space. Each agent receives an observation vector with 119 elements.
Wow, that's a lot of information to process. And I imagine it makes the learning problem much more challenging.
Absolutely. And to make things even trickier, they used a sparse reward structure in Cooking Zoo, meaning that agents only receive a reward when they successfully complete a dish, not for any intermediate steps.
Okay, so we've got these three environments: box jump to test pure cooperation, simple spread, and this challenging Cooking Zoo environment. What were the key results of their experiments?
All right, so looking at the results on the 8-agent box jump task, they found that all the models, PairVDN, VDN, QMIX, and IQL, performed relatively similarly in terms of the final reward they could achieve.
So in a relatively simple scenario, they were all able to learn to cooperate reasonably well.
Yes, but things got a lot more interesting when they cranked things up to 16 agents. In this more complex scenario, some clearer differences started to emerge. QMIX, for instance, began to exhibit some instability during learning. And independent Q learning, as you might expect, really struggled to keep up, showing very little learning progress.
Okay, so as the number of agents increased, the limitations of those baseline methods started to show.
Right. They just couldn't handle the increased complexity of coordinating so many agents effectively. Now, in the 16-agent box jump scenario, initially, it looked like VDN and PairVDN were performing at roughly the same level. But when they looked at the learning curves over longer training periods, a really interesting pattern emerged. PairVDN showed a much more significant improvement in the achieved reward over time compared to VDN.
So while their initial performance was similar, PairVDN was able to learn and adapt much more effectively in the long run.
Exactly. And to understand why this was happening, they went beyond just looking at the final reward and analyzed the actual behavior of the agents. What they found was really fascinating. In the PairVDN experiments, the agents tended to stay clustered together for longer periods, forming those towers more consistently. They argued that this was a direct result of PairVDN's ability to learn these non-monotonic value functions.
Because it could properly value those situations where the agents were acting together in a coordinated way, as opposed to just valuing their individual contributions.
Exactly. And this difference in behavior, they argue, is a key finding that really highlights a fundamental weakness of approaches based on monotonic value decompositions. When you need tight synergistic cooperation, those methods just don't have the representational power to learn those truly valuable joint behaviors.
So box jump provided some really compelling evidence in favor of PairVDN. How did it perform on those other environments, simple spread and Cooking Zoo?
Well, interestingly, all the models, including PairVDN, struggled to achieve very high performance on simple spread and Cooking Zoo.
Huh. So even with its pairwise decomposition and dynamic programming algorithm, PairVDN couldn't crack those environments.
Not as effectively as they hoped. They hypothesized that this was likely due to a couple of factors. First, the inherent complexity of these environments, particularly Cooking Zoo, with its high-dimensional observation space and sparse reward structure. Second, the relative simplicity of the multi-layer perceptron architectures they used for the agent's policies and value functions.
So it's not like PairVDN is a silver bullet that solves all the challenges of multi-agent reinforcement learning.
No, it definitely has its limitations. It seems like it's really good at handling the non-monotonic interactions that are crucial for cooperation, but it might need some help in the form of more sophisticated agent architectures or exploration strategies to really shine in these more complex and challenging environments.
Okay, so to kind of summarize what we've learned so far, PairVDN seems to be a significant step forward in cooperative multi-agent reinforcement learning. But there's still work to be done, especially when dealing with environments that have a lot of complexity and sparse rewards.
Right. But to put this into the bigger picture of research in multi-agent reinforcement learning, we've seen this really interesting progression of ideas.
Yeah, it's kind of like a story almost.
Yeah.
Like we started out with that initial, pretty intuitive, but ultimately very limited approach of independent Q learning.
Right, just pretending that each agent is in its own little world. But as we saw, that quickly falls apart when you need actual cooperation. Then came VDN, which was a really big deal because it directly addressed the scalability issue of that exploding joint action space. It did this by assuming that the value function could be decomposed into a sum of individual agent values.
And this led to being able to do decentralized execution, where each agent could just focus on maximizing its own value.
Exactly. But of course, VDN had its limitations with that simple additive decomposition. It couldn't really capture those synergistic or negatively impactful joint actions. So researchers developed QMIX, which built on VDN by introducing a more expressive, albeit still monotonic, way to combine those individual agent values.
And it used those hypernetworks to make the combination even more flexible and dependent on the overall state of the environment.
Precisely. But both VDN and QMIX were still fundamentally limited by their reliance on monotonicity. And that's where PairVDN comes in, representing this really interesting departure by throwing out that monotonicity constraint and explicitly focusing on the interactions between pairs of agents.
And this shift from individual agents to pairs of agents, it feels like a pretty profound conceptual change in how we're approaching this problem.
It really does. It's like we're finally acknowledging that the real magic of cooperation often lies in the interactions, not just the individuals. And it makes me think of this parallel in the history of deep learning.
Oh, yeah. Tell me about that.
Well, in the early days of deep learning, people were mostly using these simple linear models to approximate functions. But these linear models could only represent very basic relationships in the data. And then came this big paradigm shift with the introduction of nonlinear models, primarily through the use of neural networks.
Right. And this ability to model nonlinear relationships is really what unlocked the power of deep learning and allowed it to tackle all sorts of complex problems.
Exactly. And I think PairVDN's move away from monotonic value decomposition feels kind of similar. By letting go of this strict constraint, we open up this whole new world of possibilities for modeling much more intricate and realistic interdependencies between agents' actions. And that's absolutely crucial if we want to create AI systems that can truly cooperate.
I love these historical parallels. It really helps put things into perspective.
Yeah.
Okay, so we've covered a lot of ground here. Let's move on to our novel notions segment. This is where we like to speculate a little bit, brainstorm some potential research directions inspired by the paper we're discussing.
Sounds good. So thinking about PairVDN, this idea of pairwise interactions is really intriguing, right? But the current implementation uses this fixed cyclic pairing structure where each agent is always paired with its neighbors in the index. What if we made those pairings more flexible, more dynamic?
Oh, like instead of always being stuck with the same partners, the agents could choose who to pair with at each step.
Exactly. And they could base their decision on all sorts of things: their physical proximity in the environment, their past experience of successful collaborations with other agents, maybe even some learned measure of how relevant another agent is to their current subtask.
Oh, I see. So, for example, in that box jump environment, if one agent has already managed to reach a high altitude, it could choose to pair with an agent that's currently lower down and trying to make a crucial jump.
Exactly. They could provide more targeted assistance where it's needed most. Or in a more complex environment like Cooking Zoo, maybe an agent that's currently chopping vegetables could choose to pair with an agent that's tending the stove, creating these temporary task-specific collaborations.
Right. It's like they're forming these dynamic coalitions that can adapt to the changing demands of the task. And, it's interesting that the paper does actually briefly mention this idea of changing the pairing structure based on things like proximity in their future extension section.
Yeah, they definitely hint at this possibility, and I think it's a really exciting avenue to explore. This dynamic pairing could lead to the emergence of much more adaptive and efficient coordination strategies, especially in complex and dynamic environments where the optimal collaboration structure might change rapidly.
Right. It wouldn't be easy to implement, of course. There would be a lot of challenges, like how do you determine these pairings efficiently? How do you ensure that learning remains stable when the pairings are constantly changing? But I think the potential benefits are huge.
Absolutely. It would be fascinating to see how multi-agent systems could learn to self-organize and optimize their collaborations in this much more fluid way. And there's another interesting direction we could explore, building on this focus on pairwise interactions in PairVDN. What if we introduced explicit communication between those paired agents?
Oh, that's a great idea. Since we're already explicitly modeling the value that comes from the interaction of agent I and agent J, why not let them directly share information with each other?
Exactly. It seems only natural that if we're trying to maximize the value they create together, we should give them the tools to communicate and coordinate their actions more effectively.
Right, so they could exchange information about their intentions, their local observations, their predictions about what might happen next. And this could be especially valuable in partially observable environments where each agent only has a limited view of the overall state.
Absolutely. By communicating within these well-defined pairs, they could potentially overcome some of the limitations of having only partial information. And this communication could take many forms. We could explore things like discrete symbolic messages, where agents are sending each other signals like, I'm going to move left, or I need help with this task. Or we could look at continuous communication channels where they're sharing more nuanced information.
This connects nicely with a lot of the existing research in multi-agent communication learning, where people have been exploring different ways for agents to communicate and coordinate. But I think what's interesting about PairVDN is that it provides this very structured framework for thinking about communication. It's not just a free-for-all, where everyone is broadcasting messages to everyone else. It's very targeted and focused on those pairwise interactions.
Exactly. The pairwise structure of PairVDN could really help guide and interpret this communication. And it might be the key to making communication more efficient and effective in these multi-agent systems. Of course, we have to remember that these are still speculative research ideas. There's a lot of work to be done to actually explore the feasibility, the computational costs, and the actual performance benefits of these dynamic pairings and integrated communication.
Right, but that's what's so exciting about research,
Yeah.
right? It's all about pushing the boundaries, coming up with these new ideas and seeing where they lead. And sometimes these seemingly small tweaks or extensions can unlock huge new possibilities.
Yeah.
So to wrap things up, this deep dive into PairVDN has been really fascinating. It presents this really elegant and potentially very impactful approach to cooperative multi-agent reinforcement learning.
Absolutely. By moving beyond those limitations of monotonic value function decompositions and focusing on the interactions between pairs of agents, it opens up this whole new world of possibilities for learning much more complex and coordinated behaviors.
And the experiments in that box jump environment provide some pretty compelling evidence that this approach is on the right track.
For those of you who are eager to dive into the nitty-gritty mathematical details and all the experimental results, we'll make sure to include a link to the PairVDN paper in the show notes.
It's definitely worth a read for anyone who's interested in the cutting edge of multi-agent AI research. And as a final thought to leave you with, something to ponder. If PairVDN shows us the power of pairwise decomposition for cooperative tasks, could similar decomposition strategies be applied to scenarios where you have more complex relationships between agents? Maybe even situations where there's competition or a mix of cooperation and competition.
That's a really interesting question. It gets at the heart of how we think about decomposing these complex multi-agent problems, and it could lead to some really exciting new research directions.
Definitely something to keep our eyes on. Thanks for joining us on the Deep Dive.